Welcome everybody here to my talk, and thanks again also for the invitation to give a talk here in this very nice seminar or workshop we do have here. And again, here the talk I like to a little bit explain with you here is the semantic communications, and I like to dive deeper in some specific concepts we have worked out in the recent years when we link human decision making to semantic communication, extend semantic communication also to multitasking. So the work I'm going to present here in the next roughly 25 minutes is a collaborative work between my PhDs and my postdocs and myself here when we started actually working on that a few years ago. So nevertheless, I guess it's good to wrap up a little bit. What is semantic communication, where it actually started here? And if you look a little back to the history, right, already in the 49 with the groundbreaking ideas where Shannon came up with in his publication, A Mathematical Theory of Communication, he already stated something on semantics. He said, these semantics aspects of communication are irrelevant to engineering problem, because he was really focusing at that time on the one-to-one recovery of the source data or raw data. And any system we are currently, what we have designed since the 50s here, right? 5G, 4G, 3G, and all these kind of things were based exactly on this kind of basic idea of Shannon. Nevertheless, 1 year later, Warren Reaver showed up and he picked up exactly this kind of mathematical theory of communications by Shannon here. And he also worked out some groundbreaking ideas. And he noted first the generality of Shannon's information theory here, right? But then he introduced the first time the semantic content of messages, but the way he introduced it there was more from a philosophical perspective rather than from an engineering perspective. And since then, there has just a little kind of steps forward when it comes to semantic communication, but it pops up exactly because we, from the engineering community, identified that it's also cool to jump on machine learning, artificial intelligence, and all these kind of cool things here. And with this rise of machine learning, that brought semantic communication into place. Why? Because it's a powerful tool to implement exactly also wireless semantic communication. That's something I like to talk with you about in the next 20 minutes. Just semantic communication, meanwhile, is a really, really broad term. Okay, and here you see a quick example of a classification and also give you some indication where the work we have done in the past years and currently doing are somehow classified to here. So again, here you have here these two fundamental groundbreaking papers here I mentioned. And if you look a little bit one level down, you can classify semantic communication maybe in two big pillars here. On the left side here, you see the semantic modeling, which considers structure and logical relation of elements. So it's much more logical based. On the right side here, you see you can also use statistics here, right? That means you can tackle semantic communication more from a statistical perspective using measures from information theory here to do the semantic modeling. And you see corresponding papers here showed up in the 22 and 23 here already quite earlier here. And then if you go back a little bit down here in this track here, and the green is exactly where my department here is working on. But you see, you can again here split that up on the next level. Semantic processes, which are time variant. There, many research has been done in the last few years on using age of information of a key performance indicator for semantic processes that are time variant. On the other side, you can say semantic processes are time invariant. Okay, that's mean we are now here. And then you can again split that up. And that has been a kind of a struggle also in the community. What is really semantic communication? And one people say we use semantics, which is somehow covered in the signal or in the data we process in order to recover again the raw data. So that means you use semantic to compress, but you are still interested in the recovering of the source data and raw data. That's one thing you can do. And use semantic simulatory measures like the SIM when you address, for example, compression of images or blur here, right? On the other side, you could say, no, we are not interested anymore in the recovering of the raw data. We like to recover the semantics. The recover means you transmit semantics over the channel and try to best recover exactly this kind of semantic. And that's exactly where we are working in here. So there is semantic recovery, and that's where we use, for example, you're going to see that in a few minutes, exactly motion information measures to design the systems. And then for sure you can have here, and semantic communication is always related to task. You're going to see that. That means it's also sometimes called task-oriented communication. And then you can go extend it to multiple tasks here, but, and that's the more, from my perspective, the most important thing where semantic communication will play a key role in the future. It's for me exactly the enabling technology to link intelligences. That means it's time to link semantic communication to human decision making, and that's something we have done in the last few months here. Okay, let me start a little bit again. What is semantics? And you see here, semantics, we see it is the underlying meaning. In other words, it's the model of the world of a message S. So the model of the world, I will explain, is the semantics of a certain message S. That's the real world somehow, right? Observed the real world. And it is related to the reasoning required to perform a task. That's the kind of wording we use in order to relate semantics to tasks. I give you two examples here. Assume, for example, you have a picture like this tree here, and you have a biologist and a child, and they have to interpret an image of a tree. Exactly. This tree is the random variable S here. The biologist likes to figure out the kind of trees. That's the semantics. To analyze the flora. That's the task. Okay, and the semantics is then captured mathematically in a random variable, which is a categorical random variable because there's more than just two trees, okay, in the world. On the other side, you have a child. The child is interested in the question, can I jump from the tree? That's the semantics included in the tree, right, to show the bravery. That's the task. Okay, that means here set is again a category, but a simple binary random variable. Can I jump from the tree? Yes or no? So that's something you get already an indication is what set is, what S is here, and you're going to see that's exactly how we define at the end of the mathematical framework to deal around with semantics. But we have to include characteristics like personality, knowledge, goals, intentions of the sender and receiver, right? And this is exactly why we decided once not to go in this direction of these logical relations, right? Using really probabilistic measures here. And we capture all this information about the model of the world set and the real world observed by, for example, making pictures, images in S here. And again, here I see mostly at the end of the whole story of semantics that humans or IA agents of application use semantics in order to communicate with each other. Okay, let me dive one level deeper here, right? So we define our so-called semantic source. It's nothing else than the joint distribution here between these two random variables, S and Z here, right? And we can describe this kind of how is the real world entailed with the semantics, right? Is exactly covered by the conditional distribution of S given Z here. That's exactly our semantic source. And then we have to transmit something over the wireless channel. That's our X here. But what we do at the end of the day when we design a semantic communication system is we design the encoder and the decoder. And this is our main objective we are addressing here is to recover really the semantic variables after the transmission, not the raw data. Okay. And for sure, you can interpret this. No, where is my, here. You can integrate exactly this encoder here, right, as a joint semantic source and channel encoding structure here, and the decoder as a joint semantic source and channel decoding. Everything is described by simple conditional distributions. That's the mathematical framework, how we link everything together from the transmission up to the reception here, right, and designing that. And the wireless channel is also for sure modeled by the corresponding conditional distribution here. Okay, now how we design, but we looked a lot around how design now the encoder and decoder structure for semantic communication. And since we have done a lot of work on the so-called information bottleneck, we identified that this is exactly a good approach to design exactly this encoder and decoder. That means our major objective is here, maximize the relevant information that at most set is included in the Y here, but we often have limited channel probability capability. This means we transmit over rate limited. And that's exactly where the information bottleneck method comes into the game here. That means we can formalize exactly this problem, which is also called an information bottleneck problem here. And you see here, we like to design exactly the corresponding encoder here. Compared to classical Shannon design, is a kind of a minor thing, but it has tremendous impact in the overall design. Shannon focus on having at most S included in Y from a motion information perspective. That's the only difference. Okay, but nevertheless, you compress the things differently because of this framework we set up, which is exactly everything is bounded by this optimization problem. And then we try to solve that. And for sure, there's always already used in the machine learning world as this information bottleneck is quite computation and intractable to minimize, to maximize that. We can lower bound it by using variational inference method here, using at the end of the day a variable distribution. And because of this lower bound, exactly the decoder shows up here, right? It's this Q here. At the end of the day, you see that's the lower bound here. And if you look closer to this term, it's nothing else than the negative of the cross entropy. That means the maximization of the mutual information ends up in the minimization of the so-called amortized cross entropy, amortized overall the received signals here. And the parameters theta and phi are exactly the parameters we will learn using because we implement machine learning tools here to solve this optimization problem. So that means more we focus on the minimization of this cross entropy pieces, which is a lower bound of the maximization or of the usual information here. Okay, and we started designing, and for sure we fully rely on what I said here, the powerful tool called machine learning, or meanwhile also more sophisticated solution from the machine learning community. But you see here, one approach we came up with, it's not just one picture of the tree, for example, we made 4 pictures here, right? That means we have 4 sources. This is our semantic sources here. We have here the corresponding encoders. We transmit all this through the corresponding channels, and we have one decoder to come up exactly with an estimate of the semantics included in all these kind of, for example, 4 images of a tree. And the semantic could be, the child cannot jump from the tree, yes or no. We have a single common semantics, and this is an end optimization because we minimize this cross entropy, as I said. We use autoencoder approaches. We came up with 2 approaches from the machine learning principle perspective, supervised and reinforcement learning. You can find all the details in the papers here listed below. And we compared to classical design approach with Huffman and LWC decoding. And what you see here is roughly, first, you see here, this is the LWC performance with the Huffman, and the green and the red is exactly the semantic communication design. And you see they have some similar performance here, right? You see here the LWC is much better in the higher range here, but in the low SNR range, the compression with the semantics using exactly semantics communication as this design here is better. But the key point at the end of the day is, if you compare the number of channel users, you are in the range of 10 to the 4. While here we have only 64 and 16. That means we have here roughly 400 fewer channel users, or more than 1,000 times fewer channel users for the semantic communication. That means this kind of results gives you some indication that using this kind of compression method here implemented and shown, we can save massive bandwidth, okay? But we get some comparable performance. And that's exactly where semantics is, from my perspective, also important. It's a kind of a compression in order to compress some raw data very efficiently, focusing on the semantics to compress. And then we decided, okay, let's link it to the human decision making. And we have some psychologists here at the University of Bremen. This is really a collaboration with a psychologist here. That means the key question we tried to tackle from the beginning is how to combine SEMCOM with human decision making. And the main design challenge of SEMCOM is deliver and present the most appropriate information for accurate human decision making. And for the human decision making here, we discussed with our psychologists what is the best thing you could do here. And they are exactly experts in modeling how human decides. Okay, and they propose us to use the so-called generalized context model here, GCM. And the nice thing was, it's based on probabilistic. That means it links very well to our design based on probabilistic. Okay, that means we have a probabilistic psychology model used here. It's exactly also a conditional distribution, but there's something which is important. You see here this DHK here. This DHK represents the knowledge base. The more this human observes the model, excellent, the model observed, the better it is. How is that done? That's the math find exactly in the papers here. But you see there's some kind of model, some kind of learning using more and more observation and how you decide it in order to improve the overall performance. That's a kind of model we implemented here. And we trained also this model here using maximum likelihood criteria. And so it follows also quite well the autoencoder approach we followed in the SEMCOM design. That means we have two blocks. Here's our SEMCOM design we discussed before, and here is the human decision-making block. And at the end of the day, you can interpret it as exactly as two blocks here. One is an encoder, and one is again the decoder. And the encoder is exactly the SEMCOM design I presented before. And the overall problem we solved here is now to maximize exactly as most semantic information in this variable here. That's reflected here. You have an autoencoder design here, as I said, and this is again bounding, gives us the cross entropy, and that's nice what we see here. If you interpret this cross entropy here, you see here exactly you minimize that. That means you maximize this information. It's exactly what we like to maximize. That's here, but here you see exactly, let me say, a Kuba-Gleiber divergence. If you look closer to that, you see here this distribution, and this distribution includes this semantic encoder. And this distribution is exactly the GCM model. That means what is quite intuitive, that we design our system in the way that it matches the cognitive process reflected in the GCM model as best as possible, because we minimize the Kuba-Gleiber divergence, which is quite intuitive, that SEMCOM adapts to the human, simply saying, right? The model, okay? But it's nicely reflected also in the math. That means that's good to see that it gives us some, yes, we are on the right way, what we're doing here. The key takeaway here is the design matches the SEMCOM with the cognitive process, okay? And then we did some investigations. And for sure, as I said before, the semantic communication, the encoder is designed by using neural networks. And this is exactly, for example, the last neural network here, right? Before we deliver the information to the human decision model. And you have here the received signal as input. And what we made here, just for investigation, first, we deliver to the human model here the output probabilities. Can I jump from the tree? Yes or no? Okay, so these two, for example, for the child. And we said, come on, let's maybe deliver more, not more information, the information in another way represented by using the outputs of the last layer here before we do the softmax here. Okay, that's what we just made for investigations here. And that's the result. You see here the SNR, and you see here the accuracy of the human decision-making model, right, to decide correctly. And we use the CFAR 10 data sets and a large knowledge base already, okay? In the paper, you can find also results for lower knowledge bases. And you see now we increase the number, let me call it outputs of this last layer, which we interpret as somehow features. And you see the more features you deliver to the human here, especially in the high SNR range, you see it better rather than in the low one, right? The better the decision accuracy gets. However, which is quite interesting here, best performance when we deliver the probabilities. That means that's a really compressed information to humans. And I guess everybody of you knows, sometimes you say, can you explain me that in very simple, strict way? You compress everything down to simply tell somebody what is the key thing. That's exactly reflected in here. Rather than telling you a story about 10 minutes and you're still looking, what is this guy talking about? So you see, this is how humans behave is somehow reflected in these results, which the psychologists say, yeah, that's what they expected. When we can see that our SEMCOM adapts to that somehow, right? Because this matches much better the cognitive process rather than these features we deliver here. But finally, it's also cool to see that when we let the SEMCOM decide, just take the maximum of this probability, we get a better finally decision compared to the GCM. And that's what human says. Psychology says, yeah, as soon as the human gets into the game, you have some uncertainty. Okay. So the technical system is somehow better. It gives indication, right? Nothing more here, okay? But it's good to see that what we see as results here fits quite well to the understanding what psychologists have, which is also good to see. Okay, that's one thing here. And the next thing we have done, we said, okay, let's extend everything to multiple tasks, more than just one decision to make, simply saying, because you have multiple tasks here. So we have now multiple semantic variables to deal around with. And again, here we decided to go for this kind of autoencoder approaches to implement it and to show it what the results could be here. But we had an idea to say there might be some relations in the tasks, whatever that is and how it mathematically can be expressed, I have no idea. But maybe some tasks somehow are related to each other. Why not design the transmission and reception in the way that we have a common unit and task-specific units? So we split up design approach. That's exactly reflected here. You have here a source, the S, the tree, for example. You have a common unit, and then you have two tasks here. You have the specific unit for task 1 and the specific unit for task 2 for the encoders here, and the corresponding decoders are task-specific, delivering these outputs here. But we have rate limitation again on the channel. That's why we came up with an approach to say we use the information bottleneck method for the for the task-specific units here. That's the information bottleneck, just written in the Lagrangian way here. And for the central unit, we simply maximize here exactly distribution information between this message output here and to have at most both variables set1 and set2. This should be a set2 here, right? Included. And you see some results. First, the less limitation on a channel, the better the average task execution error rate gets. That's quite obvious. But we a little bit dive deeper into it and analyze the task specifically. And if we have no central unit, we get a worse performance. That's exactly here the black line compared to the red line, or this line here compared to the red line, the black line compared to the blue one, or this line compared with this. The better ones are always with central unit. And if you look a little bit closer to the task here and analyze the random variables behind, you see they somehow match us, not perfectly, the distribution of these semantics, but somehow. And this gives us some indication that the task somehow matches to each other, and that's why the central unit brings us some gain. We are still trying to mathematically analyze and using the right measures, which really gives us, let me say, maybe a kind of estimation of what we see here, right? For sure, some are Kubark-Leiber divergence play some role here, but we are not yet fully have understood how we interpret these results. That's something I have to clearly say here. But nevertheless, the key takeaway here that the central unit indicates a positive effect on the performance, and the separate unit compresses relevant information with respect to the channel constraint, limitation, right, while extracting the relevant information for the specific task. So you see, these are two examples what we have done in the last few years working with semantic communication, how we deal around with the semantic, the classification I have shown at the beginning here. And you see here some publications already, right? Several ones still, we have just 3 submitted recently here. And main takeaway here of this talk here and the topic on semantic, the objective of semantic communication is reliable and bandwidth efficient transmission of multiple semantic variables. We are not interested in the reconstruction of the raw data. We have done also some analysis if can both done. You compress using semantics, but is it still possible to reconstruct the raw data? Yes, we already get some indication it's possible. Okay, because of time restriction, I do not like to show this here. The key takeaways here, semantic design is more bandwidth efficient than Shannon design. SemCon can handle multiple tasks. I showed just one approach doing that. And to be honest, coming back to what I said before, personally, I see SEMCOM as a key enabler for connecting intelligences. Human or machine learning with machine learning. Agentic IA needs to communicate. We have seen also 2 talks before, 3, that, let me say, maybe once intelligent IAs communicate with each other, when not just using languages in the sense how we talk to each other as humans, SEMCOM is maybe the right way to address this kind of communication between these kind of agents here. This ends up my talk, and thank you very much for your attention. Any question?
So thanks for this interesting talk. I always wonder in those talks which use neural networks for semantic compression and channel coding. Why not split the channel coding out? So you compared Huffman coding plus LDPC codes with joint source channel coding. So first, so maybe my question has 2 parts. Do we know something about the optimality of separate source and channel coding for indirect source coding, which you're doing? And second, why didn't you do it here?
It's a good question. I fully agree on that. To be honest, we have not yet investigated from a purely, let me say, mathematical, information theoretical driven kind of approach, if it's better to split this source and channel coding using the approach of semantic as a recovery. Okay, keep that in mind. That's a big difference. I would not say because it works for S to recover S, it works for Z. That's something I would not do. This is still under question, but we not have answered this question, to be honest, right? Our major first thing was really to come up to say, let's try first give some practical, because we like to implement that somehow, okay? Sometimes you do that maybe some step further before you fully understand what is behind. That's something I fully have to agree on. That's not yet given. Okay, that means I cannot answer directly the question, is it better to go for separate channel and source coding using for the semantic communication problem? That's something not clear. Depends also on the length of the data you process. We have image processing here, right, which is a huge amount of data. Short word length, right, would be maybe also different. That's not yet fully understood. Okay. You will add something.
Well, we have discussed this with the PhD students in the group. So in exactly this problem, the source separation is of the asymptotic regime.
Yeah,
now,
that's
what we have here is effectively finite block length. Yes, we give a large image in, but what comes into the channel is 60 or 64 symbols long.
No.
Yet that was on Edgar's slide.
No. It's much longer. We also investigate. That's what I said. It's not really clear, right? It's not really clear. It's
anyhow
really
in the slide with the Huffman and the LDPC code. That is finite block length regime.
That's right.
And there the gain is because in the finite block length regime, channel source separation does not hold. Now, when you go towards the asymptotic regime and have very long block lengths, the question becomes different, because there we know from theory that it's separable, and this needs further investigation, as Armin said.
That's what I said.
For the slide with the Huffman and the LDPC code, I had a long discussion with Edgar, who created these results, and we ended up finding that channel source separation does not hold in finite block length regime. So for that particular question, that's the answer. For the more general question, the question is still open.
Yeah. So please do not use the Huffman and LDPC. That's short, right? But for the implementation of the neural networks here for the SEMCOM, actually using the machine learning approach, it was by far not fine. It was fine, quite a but long, right? That's why I'm still struggling if the separation theorem holds also if you go really to this kind of setting. It's from the, let me say, the gain comes into the, that's what I, again here, that's, for me, to be honest, it's a completely different story if you like to compress with respect to this semantic information included in the message, or if you compress in the way that you can recover the raw data, the message itself. It's exactly, let me say, what sets the boundary. And I see maybe it's not that you can pick up the results by Shannon, because he was always in the one-one recovery story of the raw data to map it one-to-one exactly to this semantic approach. And that's why I'm still struggling and not giving you a precise answer so far. Okay, that's the key point.